Assalamualaikum and good morning. We are from Group 6. Today we are going to present our group project which is about practical application in geotechnical engineers cone penetration test CPT. This is our group members which is consists of 5 people. The first one is Nur Aisyah Jamila, second one is Nurul Maisara, the third one is Nurul Nargis Najwa, and the fourth one is Nur Alia Natasha, and the last one is Siti Najiha Umairah.
Assalamualaikum and hi, my name is Nur Maisara. I will be presenting the introduction of this project. So, basically, geotechnical engineering is one of the important areas in civil engineering because every structure needs to be supported by the ground. So, why soil investigation matters? Because every structure needs a solid ground to support, and skipping this can lead to the failure such as excessive sinking, foundation or slope collapse, and also weak load bearing capacity. So next is what is CPT and how it works. It works like a cone-shaped tool is pushed into the ground at a steady speed, and it measures the cone resistance, which how hard the soil pushed back, and also sleeve friction, where the friction along the side of the tools. So why we use CPT? Because it is fast, continuous, and highly reliable soil profiling. Other than that, we can upgrade the CPT into the CPTU, which it measures the third parameters, which is pore water pressure. It is crucial for soft and tricky soils such as clay, silt, and peat, and also it reveals soil strength, compressibility, and how water drains through it. So next is the objective of this project. It is to explain the basic concept of CPT and also CPTU in geotechnical engineering. It also to analyze both method data from a selected case study to represent the result using tables, calculation, and also graph. And then is to relate both method to the result, and it's relevant to the geotechnical engineering problem and suggest suitable engineering solution based on the data. So next I will explain about the background theory for CPT. CPT is an in situ geotechnical testing method used for subsurface investigation. It is used to determine soil stratigraphy and engineering properties without soil sampling. The cone penetrometer is pushed into the ground at the constant rate using hydraulic force. It measures the QC, Fs continuously with depth. It helps identify soil such as clay, sand, and organic soil. The indication is higher QC shows a denser or stronger soil. Lower QC determine it as a weaker soil. This method is widely used for bearing capacity settlement, soil classification, and also foundation design. So next is the advantages of CPT, which is a fast, continuous for soil profiling, minimal soil disturbance, and also more reliable than SPT in many cases.
So, next I will explain the cone penetration test. Cone penetration test, or CPTU, is an advanced version of the cone penetration test. The main difference is that CPTU can measure pore water pressure during penetration. In this test, the pore pressure sensor is placed behind the cone tip to record U2 value as the cone is pushed into the soil. This makes CPTU more suitable for soft and saturated soils such as clay, silt, and peat because it helps engineers understand soil behavior more accurately under undrained conditions. Compared to normal CPT, CPTU gives a better interpretation of soil properties such as strength, compressibility, and stiffness. It also improves the accuracy of soil classification and gives more reliable geotechnical data for engineering design. Moving on to the main parameters obtained from CPTU testing. First is cone tip resistance QC. This shows the strength of the soil. Higher QC means stronger soil. Second is sleeve friction FS. This helps identify the soil type based on friction along the cone. Third is pore water pressure Q2. This is very important in CPTU because it shows the response of soil in saturated conditions. Fourth is corrected cone resistance QT, which is adjusted to remove the effect of pore water pressure for more accurate results. Finally is friction ratio RF, which is used to help classify soil types based on the relationship between friction and resistance. We move to the application of CPT and CPTU in geotechnical engineering. CPT and CPTU are widely used for soil profiling and subsurface investigation. These tests provide continuous soil data with depth, which helps engineers identify different soil layers such as clay, sand, silt, and peat. One of the main applications is in foundation design. CPTU data is used to estimate soil strength, bearing capacity, and settlement, especially in soft soil areas where failure or excessive settlement may occur. In addition, CPT and CPTU are commonly used in infrastructure projects such as roads and embankments to evaluate ground stability and identify weak or compressible soil zones. Overall, CPT and CPTU are important because they provide reliable in-situ data that supports engineering analysis and design decisions. Now, I will continue with the equipment used in CPT and CPTU. The main equipment is the cone penetrometer, which is used to measure cone resistance, slip friction, and pore water pressure for CPTU. Next, the hydraulic pushing system is used to push the cone into the ground at a constant rate. The reaction system, such as CPT rig or vehicle, provides the required force support during penetration. Push rods are used to connect the cone to the surface equipment and transmit force and data. The data acquisition system records real-time measurements such as QC, FS, and U2. For CPTU, the pore pressure system with a filter element is used to measure pore water pressure response in the soil. Finally, the computer or monitoring unit is used to display and process all test results in real time. Let's proceed to the procedure. First, the test location is selected based on site conditions and investigation requirements. Next, the CPT or CPTU rig is positioned and stabilized at the selected point to ensure safe operation. Then, the cone penetrometer is assembled and checked. For CPTU, the pore pressure sensor is also saturated and calibrated to ensure accurate readings. After that, the cone is pushed vertically into the ground using a hydraulic system at a constant rate. During penetration, continuous measurements of cone resistance, QC, and slip friction, FS, are recorded. For CPTU, pore water pressure, U2, is also measured. All data is then transmitted to the monitoring system in real time. The cone is pushed until the required depth is reached or refusal occurs in hard soil layers. After completion, the cone is withdrawn from the ground and the data is saved for processing. Finally, the results are plotted into graph for soil interpretation and analysis. Moving on to the safety precautions during CPT and CPTU testing. First, the CPT rig must be placed on stable and firm ground to prevent any instability during operation. Second, only trained personnel are allowed to operate the equipment because it involves high hydraulic pressure system. Third, all personnel on site must wear proper personal protective equipment or PPE at all times. Next, all hydraulic and mechanical systems must be checked before starting the operation to avoid any equipment failure. Finally, the testing must be stopped immediately if any equipment malfunction or unsafe condition occurs at the site.
My name is Nur Ali Natasha. For my part of our group presentation, I will cover the case study, application and data analysis. Starting with our case study examines a 3-meter high highway approach embankment constructed over a soft ground modeled directly after the condition at our research detection site. The subsoil profile consists of a highly organic 3-meter peat crust underlaid by a thick, fully saturated layer of soft marine clay. Without ground modification, constructing an embankment here introduces severe geotechnical hazards. First, the soil lacks adequate bearing capacity, meaning the shear weight of the field will trigger immediate rotational slip failures along the embankment shoulders during construction. Second, because the clay has low permeability, water gets trapped inside, guaranteeing severe long-term consolidation settlement post-construction. Moving on, we propose an engineered ground improvement solution, prefabricated vertical drains combined with stage preloading. Natural vertical drainage through soft clay takes decade. By inserting vertical PVDs, we change the drainage boundary conditions to radial path. The weight of the embankment forces the entrapped water to escape horizontally into the drains, traveling up to 0.3 meters and blanket to rain out. This forces the ground to settle and gain strength rapidly before we build the road. Also, in this slide showcase our official technical design cross-section. The PVD units are designed to fully penetrate through the 3-meter width peak layer and down 9 meters into the soft clay. They are laid out at a 1.2 meter triangular spacing grid, which is the most efficient configuration to ensure rapid consolidation across the more alluvial clay matrix. Finally, here is the official process CPTU dataset for our project. The field data points validate our engineering judgments. When the cone moves past the pit layer into the clay at 3.5 meters, the pore pressure instantly surges up to 158 kPa due to low permeability. Most critically, our calculations show that the undrained shear strength falls to a low of 90.5 kPa, which officially classifies this as a very soft clay. This constructed table is complete and serves as the baseline for my group mates to plot the continuous profile charts and execute the settlement calculations. Thank you. I will now hand over to my next group member.
Next, I will present the CPT parameter analysis conducted to evaluate the subsurface soil condition at the site. The analysis focuses on 4 important parameters, which is the corrected tip resistance, slip frictions, pore pressure, and friction ratio. These parameters help identify soil strength, soil type, and formation suitability. The first graph shows the corrected tip resistance QC versus depth. The QC value generally increased from about 0.25 MPa near the surface to approximately 1.15 MPa at 10 meters depth. This trend indicates that soil strength improved with depth. The upper layer consists of weak organic peat with low bearing capacity, while deeper layers become stronger and denser, particularly the silty clay layer at 10 meters. Then the second graph presents slip friction. The values increased from around 5 kPa to 22 kPa with depth, confirming the improvement in soil strength. The third graph shows pore pressure, which rises significantly from 4 kPa to 230 kPa. This indicates that the soil is highly saturated, especially within the clay layers. Height force, pressures such as slow drainage, and potential long-term settlement problems. The friction ratio decreased from about 3.6% near the surface to around 1.5% at greater depths. High friction ratios are associated with organic and very soft soil, while lower value indicates stronger and denser soil. Based on the CPTU parameters, the site consists of organic bed crust in the upper layer, followed by clay and silty clay, and finally a stronger silty clay or clayey silt layer at deeper depths. In conclusion, the CPTU results show that the site contains weak organic clay and soft clay in upper layers, which have low strength and high compressibility. The increasing pore pressure confirms saturated clay conditions. However, soil strength improves significantly with depth, and the layer at approximately 10 meters offers category capacity for foundation support. Therefore, ground improvement techniques or deep foundation systems should be considered to ensure long-term structural stability. That's all for me. I will pass the next presenter. Thank you. The first graph shows the corrected thick resistance QC versus depth. The QC value generally increased from about 0.25 MPa near the surface to approximately 1.15 MPa at 10 meters depth. This trend indicates that soil strength improved with depth. The upper layer consists of weak organic clay with low bearing capacity, while deeper layers become stronger and denser, particularly the silty clay layer at 10 meters. Then the second graph presents the friction. The values increased from around 5 kPa to 22 kPa with depth, confirming the improvement in soil strength. The third graph shows pore pressure, which rises significantly from 4 kPa to 230 kPa. This indicates that the soil is highly saturated, especially within the clay layers. High pores, pressures such as slow drainage, and potential long-term settlement problems. Finally, the undrained shear strength was calculated to estimate the shear strength of the clay under undrained conditions. The formula used is SU equal to QT minus sigma V over NK, which is QT is the corrected cone resistance, sigma V is the total vertical stress, and NK is the empirical contractor taken as 15. Substituting the values of 1196 kPa for QT and 137.8 kPa for the total vertical stress give an undrained shear strength of approximately 70.5 kPa. This value indicates the soil at the 10 meters depth has significantly higher strength compared to the upper soft clay and thick layers. Based on this calculation, the corrected core resistance, friction ratio, and undrained shear strength all indicate that soil strength increased with depth. The layer at 10 meters depth provides a stronger bearing, straighter, and is therefore more suitable for supporting foundation loads.
Assalamualaikum, my name is Nur Nagis Najwa. So I am going to talk our discussion for this project. So based on the CPTU result obtained from the case study, it can be observed that the subsurface profile mainly consists of organic peat and soft statutory clay. This type of soil are commonly associated with low bearing capacity and high settlement potential, which can create challenge during construction. As the depth increased, the corrected core resistance also increased, indicating that the soil becomes stronger and denser. At a depth of 10 meters, the corrected cone resistance reached approximately 1196 kPa, suggesting the presence of a stronger silty clay layer that can provide better support for engineering structure. Furthermore, the pore water pressure increased continuously with depth and reached about 230 kPa. This indicates that the soil is highly saturated and possesses low permeability. Consequently, excess pore water pressure dissipates slowly, resulting in prolonged consolidation and reduced short-term stability. The decreasing friction ratio with depth also confirms the transition from weak organic peat near the ground surface to stronger clay and silty clay layers. Therefore, without proper ground treatment, the construction of the highway embankment may experience excessive settlement or even slope instability. To address the issue, prefabricated vertical drain combined with stage preloading are proposed. This ground improvement method accelerate the dissipation of excess pore water pressure and gradually increase the effective strength and shear strength of the soil. As a result, the stability of the embankment can be improved while reducing a long-term settlement. In conclusion, this study highlights the importance of CPTU in geotechnical engineering because it provides continuous and reliable information that help engineers understand the characteristics of subsurface soil. From the analysis, it was found out the site mainly consists of weak organic peat and soft clay layers with high compressibility and low strength. Although the soil properties improve with that, the weak upper layers remain unsuitable for supporting heavy load without proper treatment. Therefore, ground improvement is necessary to ensure that the highway embankment performs safely and effectively throughout its service life. Among the available ground improvement technique, the combination of prefabricated vertical drain and stage preloading is considered suitable because it can accelerate consolidation, increase soil strength, and minimize long-term settlement. Overall, the application of CPTU data enables engineers to develop appropriate solutions and ensure the long-term stability and performance of civil engineering structure. Okay, that's all from our group. Thank you so much for listening.